paper titled Design of a Multi-Circular Monopole Antenna Using Impedance Bandwidth Cutoff Frequency. Good afternoon, everyone. My name is Sagnika, and I'll be presenting my work on the design of a multi-circular monopole antenna using impedance bandwidth cutoff frequency. I've been guided under my professor, Dr. Nella Anveshkumar. In my presentation, I'll be taking you through my motivation, the introduction, methodology, results, conclusion, and the references. So, when I speak of my motivation, I read through the works of Professor K.P. Ray, where in one of his works, he proposed a relationship between the lower cutoff frequency of the impedance bandwidth with the dimensions of a traditional wire monopole antenna. So, in this formula, you can see L and R are the height and radius of the cylinder that is representing the traditional monopole antenna, and the P is the feed gap, K is the correction factor. So he proposed that a planar monopole antenna that has equivalent surface area with that of a traditional wired monopole antenna can utilize the FL formula for any desired lower cutoff frequency. So, in my literature survey, since I wanted to work on planar monopole antennas, first thing I had to know was how to design it. One of the most important things that I came across is in reference one is that the antenna should have a short probe length because it will reduce the reactive parameters, and that way the impedance matching will be better. So that is one thing I kept in mind while making my designs. Reference 2 I've already explained in the previous slide, so I'll just move on with the third reference. I also got to know that planar monopole antennas are widely used in ultra-wideband applications, which particularly strikes my interest. So, which is why I chose this. So, now I'll introduce my work. I wanted to scrutinize this formula as a researcher. I wanted to know how accurate it is. So since antenna engineers customize their antennas based on the application, the design can increase in complexity. So I wanted to see how a basic structure behaves with the FL formula, and consequently how, if I increase the complexity of the design, how it behaves with it, and if there is any error factor that is introduced. So that is my work that I have investigated. So why did I choose the circular monopole antenna? There are two main reasons. Firstly, it's omnidirectional. That means it can cover a wide area, and it can cover all directions. So I found that particularly very interesting. Also, it has a wide frequency range, so it has a big bandwidth that it can cover. So again, ultra wideband application, so that is necessary. Now moving on to the methodology. K.P. Ray said in one of his papers, he mentioned that the surface areas have to be equal. The radiating patch of the planar antenna and the surface area of the cylinder, that is the traditional wire monopole antenna, have to be equal. So in this case, I've taken the radius of my radiating patch to be A, and I equated the surface area such that pi a square is equal to 2 pi r l, because 2 pi r l is the surface area of the cylinder. And then, because I needed the height to be same, I took L to be the diameter of the radiating patch. L is the height of the cylinder, by the way. So then, by that way, L was equal to 2a. Now I put this in the formula, and I found a relationship between R and A, where R is equal to A upon 4. Now that I got the values of L and R in the terms of A, I could solve for A by putting it in the formula. Now, ultra wideband applications have a frequency range. they start from 3.1 gigahertz to 10.6 gigahertz. So now that I'm looking at the lower cutoff, I took 3 gigahertz because I felt that it's a buffer. It's a buffer that allows the antenna to ensure that the antenna does not lose performance in the lower edge of the ultra-wide band. So that is why I took 3 gigahertz as my desired FL frequency. So after putting the equation in terms of A, I found out that A is equal to 8.83 millimeters. So now using this radius, I made a design on HFSS. It's here, it's shown here, this design I made on HFSS. And the construction is such that the substrate I use is FR4 epoxy. It has a dielectric constant of 4.4 and the dimensions I took is 40 cross 40 millimeters with a thickness of 1.6 millimeters. And the partial ground, the radiating patch and feed I took to be copper. The feed gap I kept to be 1 millimeter. So in the results, the resonant frequency came at 3.5 and 9.2 gigahertz. Moving on, I further increased the complexity of my design by adding 3 circles in a triangular fashion. Now, all of the circles have equal radius and I've denoted them by B. So now, in the similar fashion, 3 pi B square is equal to 2 pi RL. But it is worth mentioning that L is approximately equal to 4B. It's not equivalent to 4B. So that accounts for some error in the ultimate simulations. So that should be mentioned. So and then again I solved the equation the way it should be, and B was thereby equivalent to 4.54 millimeters. So using this radius, I designed this on HFSS and I simulated the design on HFSS, and these were the S11 parameters I got. The dips came at 4.1 and 8.1 gigahertz. So next design, same thing I did, and this time my radius came to be 3.056 millimeters. I simulated on HFSS. I also fabricated the design. And I calculated the S11 parameter on the vector network analyzer. So, and this result shows the comparison between the HFSS simulated result versus the VNA result. So the dips here are at 5 gigahertz and 5.42 gigahertz respectively. So now, coming to the conclusion, what I came to understand is that if you can see the table here, you see that as I increase the number of circles, the simulated FL value also increased, suggesting that there is an error factor that is being introduced. So my inference that I came is that for basic planar monopole antenna designs, the FL formula holds valid. But furthermore, when you increase the complexity, the antenna engineer must be worried before using it because there is some sort of error that will be introduced. That being said, these are my references and I'd like to thank you for my time. I am open to any questions. I'll try to answer to the best of my ability.
Over to audiences.
Already antennas are proposed for 3 gigahertz in the size of like below 20 cross 20. What size is it taken?
40 cross 40.
So as a study wise, I like that. Okay, we are establishing a relation between cutoff frequency, how we can obtain the impedance bandwidth. But in real time, we can apply this already. Their antenna is already available. About 20 cross 20, 25 cross 25 in the real time to apply for even a UWG. And then from even certain works are there which they are including 2.45 gigahertz also. So how you see this thing that in real time when we are fabricating the antenna, or how this study will help?
I think my main intent of doing this study was to keep and researchers informed that this formula used by KP Racer can be implemented, but we must be wary. Now, the design depends on the researcher himself or herself, but using this formula for a desired frequency, that has to be something that needs to be kept in consideration, and that was my main intent of doing this work.
One small comment. What is impedance bandwidth?
So
How we decide why this term is there? Bandwidth plus impedance. Impedance is different. Bandwidth is different. Why we say it's like impedance bandwidth? What it is?
so uh,
You are a UG student or PG student?
I am a BTech student,
Okay.
so I will look into it.
So,
And
thank you.
Okay, good. Very nice presentation.